Okay, so the first thing we're going to look at today is cumulative relative frequency graphs. And so it's kind of like looking at a running total of data. So as you put in more data, you're adding them up as you go along. And we'll see what this means when we do a graph down here. So the data we're looking at is the ages of the first 44 U.S. presidents when they took office. So this data is not updated. Obviously, our current president is 45th president, but I haven't updated this in a couple years, so just deal with the data as it is. All right, so what this is telling us is that there were two presidents that were aged 40 through 44. Also, remember that we don't think of age as a decimal. We think of age as being an integer. So you're 40 until your 41st birthday, and then you're 44. You're 40 until your 41st birthday, in which case you're 41. So there were two presidents in that age range. There were 7 that were age 45 to 49, and so on. If we total all these up, obviously it should be 44, which is the number of presidents that we're talking about here. Okay, so we want to talk about a relative frequency. Now, we saw this in the last chapter. The relative frequency is just 2 divided by the 44. And so then this number is 0.045. So that's like 4.5%, right? So we could continue and do a couple more of these. 7 divided by the total of 44. And that ends up giving us something like almost 16%, 0.159. What to round to? There's not really a rule. Round to what you think is most appropriate. There's no rule in AP statistics as to what you should round to. Sometimes you can round incorrectly. Like I wouldn't round this down to 0, right? I mean, that would be silly. I probably would round this up to 20%. That would probably be, silly as well. So there's no set rule for what to round to. Just use an appropriate rounding. All right, so we can continue these. I'm going to just do one more. 13 divided by 44, and that ends up being something like 0.295. So 29.5% of our presidents were between the age of 50 and 54 when they took office. Okay, so you could continue that, and you'll probably want to continue this column, but for the sake of time, I'm going to move on and talk about cumulative frequency. So this is a running total of the frequency. So there were 2 presidents in this age range. There were 9 presidents below the age of 49. There were 22 presidents that were younger than 54. And so you can see what we're doing here. We can think about, this number is going to be all of these added up, or 22 plus this 12. So 34 here. And this goes pretty quick, so I'm going to go ahead and finish the whole. So this last one is 44. So that means all 44 presidents were younger than 69. Now our current president, I think, was 70 when he took office. So I would have to update this data and put a new set of data. So didn't want to update the whole chart, so I haven't updated this yet. Okay, so then cumulative relative frequencies. So just like we did this to the frequencies, we're going to do the same thing to the cumulative frequencies. So this one is still 0.045, and so we can think about adding these things up, or we could take this number and we could take 9 and divide it by 44 if we want it. We could do it that way too. Either way you do it, it's about 20%. Okay, so it was this almost 16 plus this a little more than 4.5. So that would give us this total. So we can do a running total of these. Obviously, you'll have to finish these before you probably do these, unless you do the calculations like I'm doing here. So stop this video and fill in all of this, and then we'll proceed next on how to get to the actual graph. All right, so through the magic of video editing, I've already put all my numbers in here. And so now what I want to do is concentrate on how to create this graph. Well, remember when we do graphs, we always want to put a title. So for this title, I would put something like cumulative relative frequencies graph graph for ages of U.S. presidents, or something like that, right? At inauguration. Okay. We also want to make sure that we have our labels, our graphs labels. So this is age, age of the president, and this is going to be, we call this relative frequency. Okay. So in other words, we're not going to use the counts. We're going to use the frequency. The counts would be frequencies. We're using the relative frequencies. So these will be percentages. So I think if you see, I probably put 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you can see at the end of our cumulative relative frequencies, we're at 1 or 100%, right? That's 100%. So this will be, I guess I maybe should leave myself a little more room here. Let's put my numbers in first. So this is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and 1.0. And then let's put in, again, relative frequency. Okay. All right. All right, so how do we graph these? So you can kind of see it's customary to always begin. Well, wait a minute. Let's do our scale here too. We're going to use the same classes here. So this will be 40, and then don't go to 44. Go to the next, the next beginning of the next class, which would be 45, right? So 40, 45, 50. 55, we're going by 5s, not by 10s, 55, 60, 65, and then 70. Okay? So go by 5s there. Matches the how we're going by the classes, if we were going to make like a histogram there. Okay? All right. So now what we do is we start with the 0 on the bottom left corner. So even though there might be someone who's 40, one of these people might have been 40 when they took office, but what we're saying is there's no one sort of to the left of that. So, and then what we do is on the next one, 45, we are going to plot this. I know it seems like we're off by 1, but in this one, it's in this range. So at this point, we put the 4.5. So something about there, right? The first tick mark would be 0.5%, so this is just a little less than 0.5%. Then the next one, 50, we're going to go on the bottom side of this, right? And so that's going to be 20, 20.5, so it's something right about there. All right. I'm having a hard time showing you the numbers up above plus my graph, but let's see if I can do it. And then the next one would just be at 50. So at 55, we're going to be up at 50 here. Okay, and it does feel like you're off by 1, but you always go over 1. You start over 1 to the left essentially. Okay, so then 60 would be the next one. That would be 77. So here's 70. There's 70. We want to go up to 75, 77. So, somewhere around there. And then 93 at 65. We're going to be at 93. So somewhere here. Okay. And then the last one, well, we're at 100%. So that means 100% of the presidents were younger than 70. No one was over 70. And so then we sort of create this ogive curve. Okay? It's called an ogive curve. All right, and so now we can actually calculate some values, ask some questions about it. So here's some questions. This cumulative relative frequency graph allows us to ask some interesting questions. All right, Barack Obama was 47 when he took office. Is this unusually young? So let's look. 47 was here. So 47, that tells us that that there were only about 10%, if we go up at 47 and go up, hit the curve and read it off to the left. This is percentages. That means 10% of the presidents were younger than him. So not very many presidents were younger than Barack Obama. So yeah, that was particularly young. He's in the, what we will call it, we'll see in the PowerPoint that we're going to start, that is the 10th percentile. All right, next one. 65% of U.S. presidents were younger than what age? All right, so we're sort of going to go backwards. We started with the date here. Now we're starting with the percentage. So we want to go up to 65, which is right here, and we'll read that over, and then take that down. So, something like that or so. So something about, 58, maybe 57. 6, 7, 8. So I would say about 58 is the age about which 65% of the presidents were younger than about 58. All right, and then Martin Van Buren was 54 years old when he took office. What percent of presidents were younger than that? So we can go now back to 54, which is what here, and then we just, so 54 is right here, and then we just take that line up and over, and we estimate, maybe 42%, something like that. Okay, so he's in the 42nd percentile. That means 42% of presidents were younger than him. All right, let me go back and now erase some of these, and I would like to, on top of this graph, create a, or at least begin the creation of a histogram. Okay, so a histogram, the first one is going to be right here, right? So we've already got that one dot, so I can just kind of shade that in. And the next one, we're not going to go up to this dot because it's really the difference in those two dots is the height that we want. So we're going back up to this number, relative frequencies now, and so it's about 16%. So that's going to be, something like that maybe. Just a little bit above the 15, and so something like that. Okay, and then we could continue doing the histogram here. So the next one is just under 30, so just a hair under our 30, and so something like that. And then that would be, we saw in the previous chapter how to make these histograms, but you can see the height of this box is the difference in the heights of these two dots. Okay, so if we made a box just at the, for example over here, if I made a box between those two dots, that box, if I brought it all the way down, would be the next class width bar for our histogram. And you'll see this in the PowerPoint that you'll see in a second. It does a pretty good job of visualizing that for you. If you look at the PDF for this that I had attached to our Google Classroom, you'll see that I have a last page that has actually the graph on it as well as the data. So if you want to check that, pull up that PDF, or maybe I did it as a Google Doc, but you can pull that up and verify that you did the correct graph. And if you made a histogram, this is what it should look like, and then this is the data. All right, so we're starting the PowerPoint here for section 2.1. We already just went through an example of a cumulative relative frequency graph so that we can utilize that in this data, in this PowerPoint, so it'll kind of make more sense when we get to it here. All right, in this section, we want to find and interpret the percentiles. We're going to look at a cumulative relative graph. We'll talk about the z-scores, and then we'll talk about how the descriptions of center and the spread change when we manipulate data. All right, so the pth percentile. So the percentile is the, in a distribution, is the percent the observations that are less than the observation of interest that we're talking about. So if we look at, for example, Jenny scored an 86 on her test. We have a stem leaf plot here of all of the scores from her class. So you can see 86 there is in bold, so you can kind of see. Well, how well did she do compared to everybody else? So we would like to know what her percentile is. So if we look, there are 21 of the 25 observations that are less than her. That would be about 84%. So Judy is in the 84th percentile. Now, this isn't exact and perfect all the time. We use this percentile when we deal with lots and lots of data. So for example, let's say that Jenny got a 93 on that test. And so if she got a 93, then there would be, you might say that she's in the 100th percentile. But if we look at the definition, 24 of the 25 people did worse than her. So 24 divided by 25 is 96. So even though we kind of know, yeah, well, she's in the 100th percentile, right? Because she's on the top. So we use percent, so it's off a little bit, right? So these are sort of estimates. It makes more sense when we're dealing with large numbers of data values, like everyone who took the SAT last year. You could be in the 100th percentile. That means you have the top score, right? But that's because you have maybe 1 million people that took it. And if you're on the top score, then that means 999,999 people did worse than you. And then you, of course, would take that number and divide it by 1 million, and it's pretty close to 100%. So these are estimates. Just know that. All right, on this slide, we're going to look at the cumulative relative frequency graphs. Now, we already looked at this on the worksheet before we started the PowerPoint slides, but so we can just run through this. We're going to practice it a little bit more again here. All right, so we have the ages of the first 44 presidents when they were inaugurated. We looked at the frequency. We looked at the relative frequency. We looked at the cumulative frequency, and we looked at the cumulative relative frequency. Look back on your worksheet that we just looked at, and we created a graph from that, and it's called an OG curve. And so we can use that to answer some questions in the next slide. All right, so let's ask some questions. We already did some on our worksheet, but let's do a couple more. What percent of presidents were younger than 50? All right, we can see that pretty easily is 20. If we go up from the age 50, you hit that dot right about 20. It's maybe just a hair above 20. All right, now approximate Q1 and Q3. Remember that Q1 is simply the 25th percentile, and Q3 is the 75th percentile. So if we go use our lines to kind of go over like we did before, we can see where we would get about 51 and about 59, okay? And then working backwards, approximate the age under which 80% of the presidents were inaugurated. That way we could just go straight over from 80 and go down, and we would see that that's, about 61, maybe if you said 62, okay? So again, a histogram, if we think about the histogram, we would take these values, the difference in all of these, if we wanted to make a histogram, the difference in heights of all these dots, and bring them down, and that would be the histogram that you saw on the other page that we were previously working on. All right, one other way to talk about your position or a data value's position in a distribution is to look at the z-score. The z-score is simply the data value minus the mean of the whole distribution divided by the standard deviation of the distribution. So that z tells us how many standard deviations above the mean you are. So let's look at an example. Let's go back to Jenny's example. And so we didn't give you this information before, but now we're telling you that the mean of the test score, the mean test score of her class was 80, and the standard deviation of her, remember, standard deviation is a measure of spread. It's how, it's the typical difference between the scores in her class and the mean in her class, right? So the standard deviation for her class was 6.07. we want to know what is her standardized z-score. All right, so it's just her value minus the mean, and then we divide that by 6.07. That gives us about 0.99. That is not, remember, this is not a percentile. She's not at the 90th percentile. That 0.99 is close to 1. That means her test score is just shy of 1 standard deviation above the mean. So you can kind of see that, right? She's 86. She's at 86 here. The standard deviation is 6 above the standard deviation is 6, and that's just about 6 above the mean, which is 80. So she's right at 1 standard deviation above the mean. All right, let's look at another example for z-scores. Jorge is in Mr. Rogers' trig calc class, and Santi has Mr. Rubin. Both teachers gave their own Chapter 4 test to their own class. Mr. Rogers' class's mean score was a 75% with a standard deviation of 4.7%. Mr. Rubin's mean was 65% with a standard deviation of 6.2%. So that means Mr. Rubin's scores were more spread out than Mr. Rogers' scores because his standard deviation was larger. All right, so Jorge, who was in Mr. Rogers' class, got an 84%, and Santi, who was in Mr. Rubin's class, got a 79%. So compare each of those two students' scores to their own classmates. Who did better? Now, clearly, Jorge got an 84, and Santi got a 79, but relatively speaking to their own classmates in their own classes, who did better? And so what we want to do here is look at z-scores. So calculate each of their z-scores. Okay, so you can see that Jorge's z-score is 1.91, so that means just a little shy of 2 standard deviations above his class's mean. If we do the same thing for Santi, we see that his z-score is 2.26, so he did about 2.25 standard deviations above. So even though Jorge's score, ultimately 84, is better than a 79, Jorge did not do as well relative to his own class as Santi did relative to his class. So Santi scored more than 2 standard deviations above his class mean, whereas Jorge scored less than 2 standard deviations above his mean. So clearly Santi did better when you compare them to their relative classmates. All right, so we have some homework. I think because we have so much more time, I think we're going to go ahead and continue working on the next section, next part of this section. And then, so you'll have 2 homework assignments. You'll have 2.11 and 2.12, 2.1.1 and 2.1.2, both due next class. All right, so this one's pretty straightforward, but let's say I asked everyone in class, assuming we were actually in a classroom, what is the width of our classroom in meters? And then these are the guesses. So this is a dot plot of all of the guesses of everybody. So some people guessed as low as, 8 meters, and some people guessed as high as 40 meters, right? If we wanted to describe this distribution, remember we use SOCs, we use the shape, the outlier, we talk about the outliers, we talk about the spread, and we talk about the center in no particular order. So this is clearly skewed to the right. I would say the center. Now it would be wrong to say the center is right here in the middle, it looks to be about 15, but it wouldn't be right to say the center is 15. We have to say something like the mean or the median is 15. In this case, it would be the median is 15. Also, I can't say the spread is a certain value because we measure the spread using things like range or standard deviation. I think in this case I'll just use the range. And so we go from what looks like 8 all the way up to 40. So it looks like we have something like a spread of 32. Now remember, we don't say the range. The range is 32. We don't say things like the range is from 8 to 40. Range is a single number. it's the max minus the min. So it would be wrong to say the spread is 32. That would be wrong. You would want to say the range is 32. It would also be wrong to say the range is from 8 to 40. Range is the maximum value minus the minimum value. So it's recorded as a single value. There does appear to be outliers. You know, in the right end or the high end, there does appear to be outliers. We could, you know, we're just asking to describe the distribution, so we may not have to necessarily find which ones are outliers, which ones are not. You could if you wanted. So let's see, we did center, we did shape, we did outliers, and we did spread. So we did the 4 things that we are required to do. And now let's look at what happens when we transform the data. So here again is the dot plot of all of the guesses in meters. And so the true width of the classroom, let's say the true width is 13 meters. So instead of recording everyone's guess, I might want to let them know how off they were from the true value. And so here we have the error. So in other words, 13, so again, 13 would be right here. So 3 people guessed 13. Notice those 3 people are right here on the 0 mark, right? So we transformed this data. We shifted it essentially 13 units to the left. We are using the same scale in both cases. Notice some values of the guesses, some people's guesses are negative, or I'm sorry, their error is negative because they guessed below the actual value. So anyone who guessed in the range of 8 to 12 would have negative error values, and you can see they showed up in the negative range down here. Okay, let's look at the actual data summaries for the 2 distributions, one the guess and one for the error. What values are the same and which ones are different, and by how are they different? So if we look, the spread, if we just look at the 2 dot plots, you can see the spread really hasn't changed. So the range, the interquartile range, and the standard deviations are all the same, right? All of those 3 are the same. So the measures of spread that we're using have not changed by shifting the whole distribution down 13 points. But notice the measures of location. So like the minimum, the maximum, Q1, Q3, the median, and the mean. All of those measures of center and position did change, and they indeed changed by exactly 13. So if we kind of tie it all up, I think your slides on your handout were in reverse here, these 2 slides. So what happens when we add a number or subtract a number, A, from each observation? Well, it adds or subtracts A from the measures of location and center. We saw that. The mean, the median, the quartiles, Q1, Q3, the percentages would all change by that same value. However, the spreads do not change. All right, so now let's say, you know, if I said, oh, your error was 2 meters. Well, some people don't really have a good sense for what 2 meters are. So let's take our data and convert it to feet. And we know that there are about 3.28 feet in 1 meter. So if I convert by taking each error value and multiplying each one by 3.28, I would get this. Now notice I'm using the same scale, right, on the bottom here. If you guessed 13, remember you would get an error of 0 meters. You would also get an error of 0 feet, right? So I'm trying to draw an arrow, that's not working. But you notice that those values did not change. But all the other values got a little bit more stretched out. Notice the spread of these dot plots are very different. And so the range, for example, if we want to look at the range, what happened to the range? Before it was 32, and now it's 100 and almost 105, right? So obviously that changed. And you notice all of these values changed. How did they change? Probably you can pretty quickly see that they all changed by a factor of 3.28. Sure enough, how many feet are in a meter? So each thing got multiplied Each data value got multiplied by 3.28. Each of our number summary values got also increased by 3.28. All right, so let's tie it all up. So what's happening here? What happens when I multiply or possibly divide by each observation by a given number, and in this case we're just going to call that number B. So in our case we multiplied by 3.28, that's our B. It multiplies or divides the centers. So if I was dividing by, let's say I started with meters and feet and I wanted to convert to meters, then I would divide by 3.28. The reverse would happen, right? So instead of being more spread out, it would be less spread out. All right, so in this case you're multiplying or dividing, depending on what you did, each of the measures of the center, but also you'll be doing the same thing with all of the measures of spread. So the spreads all get multiplied. Now, one little caveat here is that I suppose if you're going to multiply, you might be multiplying by a negative number. Can't think of an example off the top of my head, but if you're multiplying by a negative number, measures of spread cannot be negative, right? So the spread was 32. Notice I'm not just going to take that and multiply by B, which might be negative. So in this case, you have to do the absolute value of B because measures of spread are always positive. Standard deviation, range, interquartile range. Always the maximum minus the minimum for range, so it cannot be negative. Even if you multiply through by a negative number, the measures of spread would get multiplied not by B, but by the absolute value of B. All right, and then of course the shape still didn't change. If we looked, both of those distributions were still skewed to the right. So the shape didn't change, but they got more spread out, but the shape is still the same. All right, so here is your other homework. So both of these homework assignments, 2.1.1 and 2.1.2 will be due next class.